Hello class, in this video, this will be an introduction to graphs of circular functions. The learning intention for us to explore the new features of the graphs of circular functions and to learn the vocabularies associated with these key features, including the amplitude, the period, domain, as well as the range. Now, before I show you the graphs of sine theta as well as cos theta, I want to show you how this is kind of related back to what we know of the unit circle. So if you guys recall, the unit circle is really useful for us to find out what is the x and y value of a coordinate found anywhere along the unit circle. So for instance, if you want to find out what this particular coordinate is on the unit circle, we know that the x value of that particular coordinate is equal to the cosine of that theta. So that's what this represents over here. Whereas the y value can be determined by finding what is the sine of that particular angle over there. Now, if you're finding out what that position was, or this position even, we know that because the unit circle has a radius of 1, we know that the x and y value will lie in between the values of -1 as well as +1. So it's within this particular restrictions over here. Now, the thing is that the x value as well as y value can be plotted to see how these values kind of change over time as we actually change what the angle is. Okay, so if it was 45 degrees, what is the x value? If it was 170 degrees, what's the x value? We can kind of plot the exact value of the x value to versus its theta to see how these values changes. And if you actually plot this graph, we refer to these graphs over here as circular functions. So over to the next slide over here, this is what the graphs of circular functions will look like. So if you were graphing cos theta versus theta, or sine theta versus theta, you're going to be producing these waves over here, and these waves are referred to as sinusoidal. So that's just a technical word that describes the symmetrical wave or the symmetrical graphs that's produced by cos theta as well as sine theta. We'll talk about what the graph of tan theta looks like in future lessons, because that's a bit more harder and it doesn't actually follow this wave like pattern. Okay, so over here on my left hand side, I've said circular functions are functions, so just equations describing either the horizontal, which refers to the cos graph, or the vertical positions, which is sine of a point on a circle as a function of an angle. The simulation on the right hand side kind of shows you how you obtain each of the graphs from the unit circle. So starting from here, if we're just looking at the cosine, okay, cosine is related to the x values, and it's showing you how does the x value of the point changes as you move across. We know that the x value for this particular point over here is going to equal to 1, but as it moves over here, that's where the origin is, we know that this particular point over here, the x value is equal to 0, and that's kind of mapped out by this as well. Notice over here, let's just wait when it goes over here or over here, the x value should be over here, and as you can see, it's over there. As it moves back over here, it's going to be equal to +1. When it moves over here, it's equal to -1 as here. And the same thing shows for the sine graph as well. We know that sine is related to the y value, and the y value should be equal to 0 when it reaches this particular point or this particular point, which is also mapped over here as well. Now, we also refer to as sine and cosine graphs as periodic because they repeat themselves at regular intervals. So what that just essentially means is that if you go more than one circle around the unit circle, then you're going to be producing the exact same pattern. So these are the properties of this sine function. So this is the most basic sine graph, and we refer to it as the parent function of the sine function. And that's just where you have no transformations applied to it at all. So you don't really have any dilations or translations whatsoever, or reflections. So over here, the domain of a sine function, which just means the set of x values that's shown for a basic graph over here, it starts from 0 all the way to 2 pi. And remember, 2 pi is equivalent to 360 degrees. So you could write that as 0, 2 pi or 0, 360 degrees. But remember, I said that we generally use in radian form, generally speaking, when you do more difficult maths, okay? The range on the other hand is between -1 and +1. So we can kind of see that on this particular graph over here. So the range, all the possible x values lies between 0 to 360 to 2 pi, and all of the possible y values lie between -1 and +1. We can clearly see that your x-intercept is going to be starts from 0, pi, which is equivalent to 180, and 360 as well, whereas there's only one possible y-intercept. And again, just to show you how do we actually obtain the sine graph, remember sine is related to the y value. So remember that the y value is going to equal to 0 when it's around here, when the coordinates are around here, but it's going to equal to +1 when it's here, and it's going to equal to -1 over here. So if I play the animation, notice that your y value is greatest when it's over here, but it decreases when it's there, and it goes back to 0 when it's at 360 degrees again. And what I'm showing you on the next slide is, this is a graph showing it to you in degrees mode, but you can change the scale of your axis to make it into radian form. And this is what we generally do it. So I just want to get you used to seeing this particular notation over here. Just recall that unlike all the graphs you've looked at previously, for sine, cosine, and just circular functions in general, you will generally encounter more than one x-intercept. So it's not unusual, okay? So this particular sine function is a kind of a elongated sine function. Now remember that for the most basic sine function, the domain stops up to 2 pi, but as you can see over here, I've kind of stretched it and continued the pattern onwards. So in this case over here, since we know that 2 pi goes around one revolution of a unit circle, since I'm showing you all the way up to 8 pi, how many times do you think we have to go over the unit circle in order to draw this particular graph over here? In this case over here, because we're going through 8 pi, it makes sense that we're going to be going over 4 times. So that's 1 time, that's 2 times, that's 3 times, and that's 4 times. So by repeating the unit circle 4 times in an anti-clockwise manner, you'll be able to draw this particular graph over here. And that should be 7 pi, 0 right there. And there should be 8 pi, 0 as well, but for some reason that's missing. Okay, so the next graph we're going to be is cosine. Similarly, the domain of this one here is between 0 and 2 pi, which is 360 degrees. Similarly, again, the range, all the acceptable y values starts from -y all the way to +y. And in this particular case, your y-intercept is at pi on 2 and 3 pi 2. Do you have to remember this? No, don't actually remember. This is not, the x-intercept and the y-intercept is not particularly useful for you to know, but it's really important that you do know what is the domain and range as well. And this also applies for the sine graph. If you're wondering how do we derive the cos theta, we can obtain this from the unit circle. So remember, cos is mapping out what is the x value of a coordinate as you move along the unit circle. So we know that the x coordinate is going to become +1 here, -1 when it's over here, and 0 when it reaches this particular point over here. And that's shown in this. So it goes from 0 when it's over there, 0 when it goes over here as well, and it goes back to +1 over here. Similarly, on this diagram over here, I'm showing you what is the radian equivalent, because I want you to get used to labeling your x-axis in radian form rather than degrees, because that's what's used in more sophisticated and higher level mathematics. And on this particular slide, this is just showing you a diagram comparing sine theta as well as cos theta graphs, okay? As you can see, both of these graphs are pretty much identical or very similar in terms of shape, because they do produce a wave-like function or a wave-like pattern. And one of the ways that you can differentiate between a sine graph versus a cos graph is that the sine graph always starts from the midpoint, okay? So notice over here, this is the midpoint or the midline of the graph, and the sine graphs will always start from the midline, whereas cos graphs always starts from one of its peaks, okay? So from either its maximum peak or its minimum peak. So that's one of the ways that you can differentiate between these two graph types. So you're probably thinking, what's the point? I spelled graphs over here wrong, but what's the point of learning about sine graphs and cos graphs? And the reason why we actually need to learn this is because, generally speaking, the reason why people study higher level maths is because They want to find an equation that represents or models real life situations, okay? And we could use these equations or graphs to represent some of these real life world processes. For instance, you can actually use a wave-like graph to show the patterns in the number of daylights in a month or a year, the weather patterns, tidal activities, and other circular motion. So for instance, what's the height of the person on a Ferris wheel over time, for instance, okay? And scientists and other data analysts observe this back and forth movement for them to collect data, and they represent this using an equation, so in terms of sine, in terms of cos, and this will help them answer certain questions that they're after or they're wanting to find out. So that's the reason why we're learning about this. So before we continue on, I want you to quickly answer this question over here. I want you to identify which graph corresponds to a sine graph and which one corresponds to a cosine graph. Give yourself 1 minute and we'll compare our answers together. If you guys have answered this correctly, because this starts at a peak, this is going to be a cosine graph, and whereas because this starts at the center or the middle of the graph, then this is an example of a sine graph. We're now going to be looking at the general equations of a sine graph as well as cos graphs. So this is the general equation for both the sine graph as well as the cosine graphs. Now, something that I do want to point out firstly is that different textbooks, they use different letters. So instead of having A, B, C, and D, they might use like A, H, K, those kinds of pronumerals instead, but they essentially mean or represent the exact same thing, okay? So, but in this case, I'm just going to be using the pronumerals in alphabetical order, A, B, C, and D. And each of these pronumerals have a different effect on the shape, the position, and the size of the graph. So these are effectively transformations to the actual sine and cos graph itself, okay? Now, based on your understanding of transformations and the quadratic turning formula, you should know what A, C, and D do in terms of the shape, size, or position. So if you guys recall, this is what the general formula of the quadratic turning point formula is going to be. And this is a nice acronym to remember the transformation. So Dr. T, so dilation, reflection, and translations. And as I said, A, C, and D and K, these are very similar. So if you understand what this turning point formula expresses, then you should understand what each of these letters represent as well. So have a go and tell me, what do you guys think will happen if the value of A is changed? So what do you think A does to this graph? Does it change the size? Does it change the shape? Does it change the position of the graph? Tell me, what do you think A does? In this case over here, I'm hoping that you guys can recall that from the quadratic formula, changing the value of A changes the actual size. So you're either making things wider or smaller, or stretching it or making it more narrow, okay? But I do want to point out to you guys that in this particular topic where we're looking at circular functions, we don't actually use the word dilation to describe changing the actual size of the graph. We actually use the word amplitude instead. So look at the animation over here. In this particular animation, I'm going to be changing the value of A. At the moment, my A value is 0, which is why 0 times sine, that's just going to give you 0. That's why I've got a horizontal straight line. But notice what happens when I change the value of A. When I increase the value of A, notice that I'm making the graph a lot more larger, okay? So that's what I mean by here. Increasing the value of A increases the distance from the midline. So the midline is essentially an imaginary line, okay, that goes through the middle of the graph. So the distance between the peak and the midline increases as I increase the value of A. In contrast, if I actually make the value of A negative, similar to what we've learned previously, this actually reflects the actual graph itself. So it actually flips it. So this is shown over here. Notice as the A value is negative, instead of going in this particular direction, it's now going in this particular direction. And similarly, if you make the A value more negative, so making it by -5, -10, this actually makes the peaks a bit more further away from each other as well. Now that we've gone through how does A change the graph, can you guys tell me, how does the value of C and D affect the shape and size for this particular graph over here, based on your knowledge of the turning point formula. If you guys have answered this correctly, then changing the values of C and D changes the horizontal and the vertical placement of the actual graph itself. So horizontal translation occurs when you change the value of C. So that's the value inside the bracket. So if you have a number inside of here and you change that, then you're going to be moving the graph left to right. Whereas when you're changing the value of D, which is a number found outside the bracket, then you're going to be shifting the graph up and down the vertical y-axis, okay? In this case over here, they've used the values H and K. So remember, as I said, different textbooks, different websites, they use different pronumerals instead. But in this case, H is the same thing as C, and K in this case is the same thing as D, okay? So I just want to get you guys to see what happens when I change the value of C over here. So as I change the value of C, notice that it's shifting the graph this way if I make the C value bigger. But when I make a C value negative, okay, then it's going to be moving my graph in this particular direction instead. Notice over here, when I'm increasing the value of D, it's moving the graph up, and that's shown over here. But as you make it negative, okay, then you're going to be moving it down. Now, this is something completely different to what you've already learned. So in this case, what I'm going to be doing is I'm going to be playing this particular simulation. And in this simulation over here, I'm going to be increasing the value of B. So the value is essentially the coefficient, you could say, in front of X. So tell me what happens as this coefficient increases, okay? So in this case over here, notice over here, I'm increasing the value of my coefficient. Okay, tell me what actually happens to the graph itself. Now, in this case over here, I'm hoping that you guys can see that by increasing the value B, what essentially happens is that this compresses the graph. So therefore, because you're changing the size, this is an example of dilation. And what also happens is that you're increasing the frequency, meaning that you're increasing the number of cycles within the actual graph itself. So because this is an example of a sine, one cycle goes like this. And we can clearly see that, I'll play the video again. So as my B value increases, the number of cycles you can see increases in the graph as well. So what we're now going to be looking at are the features of sine as well as cosine graphs. So these are all the different features that we're going to be going into a lot of detail. So we're going to be looking at what the amplitude is, period, minimum, maximum values, domain, as well as range. And we've kind of talked about some of them previously. So the very first characteristic that we're going to be looking at is the amplitude. And the amplitude is essentially the distance from the middle or from the midline of a wave graph to one of the peaks. So in this case over here, the middle or the midline of the graph is at this particular point of here. So the midline is essentially an imaginary line that runs through the middle of the graph. And all you need to do to find the actual amplitude, it's referring to the distance from this midline to the tallest peak, or the distance from this line to the lowest peak, okay? And because distance cannot be a negative number, make sure that your amplitude, when the question asks you what the net amplitude is, it's always going to be a positive value, okay? Now, you can actually find the amplitude of a circular function in two different ways, depending on whether they give you an equation or a graph. So if they do give you an equation, okay, well, obviously the A value, the value in front of sine or cosine, is going to tell you what the amplitude is going to be, okay? So that's pretty easily. However, if they do decide to give you guys a graph without the equation given to you, then you're going to need to do something else instead. What you need to do is you're going to have to kind of count the number of units between the midline and either the minimum or the maximum value. So for instance, let's just say that this wasn't given to us over here and I had to find this out. In this particular example, because there's no vertical translations, this is a bit easy. I can clearly see that, okay, that moves up 1, 2, 3, 4. But what would happen in a more complex example when you've got vertical translation? So let's just say this example over here. Again, it's been giving me the equation already, so I can easily say that my amplitude is going to be positive 2, although it's a negative sign here. Remember, amplitude is a distance, so therefore it's always going to be positive. But if you were trying to find this out, if let's say that this equation was not given to you, then what you would need to do is find where the midline is going to be first and then count the number of units, okay? In this case over here, you could easily say that it's going to be over here, but another way that you could kind of mathematically approach this for more complex examples is you just need to find the average between the minimum and the maximum. By taking the average between the minimum and maximum, that will give you the middle line. And once you do that, then you can count the number of units from the midline to the maximum value. So for instance, your minimum value is -5. That's the lowest y value, and your maximum, your largest y value is -1. So if you take the average, say -1 plus -5 plus -1 divided by 2, that's going to give you -4 divided by 2. Therefore, it's going to be at -2. So therefore, the average between these is going to be -2. So what that essentially means is that you need to move 2 units up or down from the tallest peak. Not the value is going to be -2. So that's just one thing to note down though. So yeah, the only thing I really want to emphasize on this page is that in this case, because I've given you a negative value, just make sure that even if there is a reflection, amplitude must always be represented as a positive value. So have a go with answering these 2 questions over here. Give you 2 minutes and then we'll compare our answers together. So in the very first question, this has already given us what the equation is for the circular function. And because it's given us the equation, then we could readily identify what the amplitude is by saying what is the value of A. In this case over here, remember amplitude must always be a positive value. So therefore your answer is going to be +3, okay? So therefore it means you're going to either move 3 distance up or down to get to one of the peaks. Question 2 gives you the graph. So in this case, you need to kind of eyeball what the amplitude is. So remember, it's the distance from the midline, and in this case over here, this is the midline to the tallest part. So therefore, it's going to be 2. The next feature that we're going to be talking about is a period, and this is something that's completely different and something that you've never encountered before. So we refer to the period as a distance required for the function or for the graph to complete one full cycle, okay? So how do you know whether something has a full cycle? Generally speaking, for sine graphs and cosine graphs, the way that you kind of measure, I suppose, the period is a bit different, but you always start from 0, okay? So in this case, sine is from here to here. So when it makes this particular part over here, we refer to that as a period. Whereas for cosine, similarly, you start from 0 as well. And in this case, it's pretty much when you go from the maximum peak to the next maximum peak, okay? But generally speaking, it doesn't really matter where you measure it from, because you can measure from anywhere, but as long as you measure it properly, then you should get the same answer. And this is probably the best way that I recommend you to memorize it. So we refer to the period as the distance from like the tallest peak, the maximum peak, to the next maximum peak. So even if for sine, notice that they've defined it or measured it in this way. Even if you measure from there, that's the same thing as measuring it from here all the way to here as well. So that's still going to be the same distance, which is going to be 2 pi as well, okay? So in order for you guys to work out what is the period, there is a formula that can be used for sine and cosine functions, and that's going to be 2 pi divided by b. And b is the value that's being given to you in the equation. B kind of tells you like the frequency in this case over here. So let's just say hypothetically that this is the equation over here. We can kind of find out the period 2 ways. We know that your period over here is equal to 2 pi and 3 because firstly it's a cos graph, so it goes from a tall peak to another tall peak. So therefore we can clearly see that's 2 pi and 3, but you could also kind of prove this by working out, and that's the way that you should always be doing things. So because the formula is 2 pi on b, in this case your b value is the coefficient in front of x, so therefore you substitute that in, and therefore that's the period over here. And once you know the period, that's how you can actually graph these bad boys, which we'll be doing in future lessons. So have a go with answering these questions. Give yourself 2 minutes and then we'll compare our answers together. If you guys have answered the first question correctly, because it's given you an equation, then what you should be doing is be using the formula. So go 2 pi divided by b. In this case, your value of b is 5, so divided by 5, hence your answer is going to be b. For question 2, similarly, they've also given you an equation over here, but this time they've given you a fraction, and that's where some students might get it incorrectly because you might not be very confident with dividing by fractions. So remember, the formula essentially is saying 2 pi divided by b. So it's essentially saying, another way of rewriting that is 2 pi divided by b. Now, in this case over here, because I'm dividing by a fraction, I could write it like this, right? I could write that as 2 pi and 1. And if you guys remember how to divide fractions, what you do is you invert this, you flip that fraction to second fraction, and you change the sign to a multiplication, and then just multiply things horizontally. Hence, your answer is going to be 4 pi and 1, which is the same thing as 4 pi. So therefore, D is going to be the correct answer over here. The next thing we're going to talk about is the minimum as well as the maximum value, and this is something that you should kind of know already. So the minimum essentially refers to the smallest y value, whereas the maximum refers to the largest y value, okay? I want to tell you what a common mistake that students often make, and it's that many students often think that your minimum or your maximum values is always going to be either the plus minus of your amplitude. So in this case over here, notice that you've got a value of 1 in front of sine x as well as cos x. Students often think that your minimum maximum is going to be +1 and -1, which is, you know, fair, and that is the correct answer for this particular example over here. But that will only be true if there is no vertical translation, okay? So if your value of d, okay, if you remember the general formula, so let's just write one for sine. If your general formula, okay, if your value of d, so there's no constant outside of it, is equal to 0, then this will work. But if there is a vertical translation when d does not equal to 0 and equals to any other value, then you can't really use this method instead. So there is another way you can find out the minimum and maximum value if the graph is not actually given to you, okay? So this is the formula over here. Minimum is equal to the negative of the amplitude plus d, where d represents the vertical translation, and maximum is going to be equal to the positive amplitude plus the vertical translation. So in this case over here, let's just say that I haven't been given this graph over here. So if I was to substitute things in, my amplitude in this case is equal to 1 because that's the value in front of cos. So it'll be -1 to find the minimum, +1 because that's the value of d over here. -1 plus 1 is equal to 0, and I can clearly see that that is my minimum value in this case because that's supported by the graph. To find the maximum value, instead of going -1, I'm just going to be adding up a +1, so therefore that equals to +2, and we can clearly see, well, it's not really shown because the scale is not there, but that's equal to +2 in this particular example over here. So make sure that you do copy down these formulas. So have a go with answering this question over here. So this question wants you to find the maximum value. Give yourself 2 minutes and then we'll compare our answers together. If you guys have done this successfully, then you should have been using this formula over here. Find the amplitude and the vertical translation. In this case, the amplitude is 10 units and your vertical translation is moving 25 units up. Therefore, your maximum value will be equal to 35. Hence, D is the correct answer. The last thing that I want to talk about is the domain and range. And these are two pairs of words that you're going to encounter very often when you do VCE maths. So the domain refers to the set of possible input values. You're probably thinking, what the hell does that mean? But essentially, if you have the graph right in front of you, the domain is pretty much the list of all x values that's being represented or shown on the graph. In contrast, the range is all the possible output values. Instead of showing the x values, which is domain, the range only refers to all of the y values that's shown on the actual graph itself. So as you can see over here, your range is all the y values that the graph could possibly be. And in this case, it's confined in this particular space over here. So between -1 and +1. So that is your range, okay? And the way that you write your range could be in this particular notation. So your domain in this case over here is all of the x values, okay? So in this case, your x values is shown from this particular point, which it's not shown to you clearly, but you can still work that out, and this particular point. And because it keeps going up by pi on 2 as an increment, then to find out this value, I just go 2 pi plus pi on 2. And similarly for this one, I can go -2 pi on -2 pi plus, minus pi on 2 to get the next value down over here. Now, one thing that I do want to mention to you guys is that there are two different ways of expressing the domain, and I don't want you to be confused. And you can write it in any way, but sometimes different textbooks questions write it in different forms. So you're going to have to be used to seeing these two different forms, okay? In this case over here, you could either write your domain and range in this particular format, which is kind of done already in this particular example over here. So what you would do is just put the minimum and the maximum limit in this case for your domain for x values as well as for your range. Or alternatively, you could use the square brackets and just substitute the values in. So what is the minimum value and then comma the maximum value. So for instance, in this case over here, if I did the math, which I kind of told you beforehand, your domain for both of these functions is going to be between negative 5 pi on 2 and 5 pi on 2. So that's using this particular method over here. Or alternatively, I could write my domain like in this particular form. So in this case, I could write it as negative 5 pi on 2 less than or equal to x less than or equal to 5 pi on 2. Up to you guys. So I want to quickly summarize what we've kind of went through in today's lesson, since this is a huge topic. So we've looked at sine as well as cosine functions, okay? And we looked at the key characteristics and what each pronoun will kind of represent. We knew that we found out that the amplitude refers to the distance from the midline to the peak. And when you're asked what is the amplitude, this will always be a positive value. Your amplitude corresponds to the value of A in the general equation. The period, on the other hand, is the distance to finish one full cycle. And the best way to think about that is the distance from one max peak to the next or adjacent max peak, okay? And the way that you would have to calculate this is by going 2 pi divided by b, where b is always going to be the coefficient, the number in front of x. C and D in the equation represents a horizontal and vertical translations, and we'll talk about this more in the next lesson, but we don't really call them vertical and horizontal translations when we do circular functions. They have a different name instead. And we talked about what the domain is, and we said that domain is all the possible x values, whereas the range is all the possible y values illustrated on the graph. What I'd like you to do now is I want you to please have a go with answering these questions over here. The questions that I really need you to do is questions 1, questions 2, 3. You can skip questions 4 and 5 because they don't really have like these identical sine graphs or cos graphs, but that's just like the real life world. Nothing is symmetrical. So you can kind of skip questions 4 and 5 if you like, and answer question 6. So these are questions I highly recommended. This is the end of today's video. Hopefully you found this video helpful. I'll see you guys again in the next video. Bye.